Hi guys, so what we're going to do today is we're going to look at how to find zeros for polynomials and factor polynomials similar to what we did yesterday, but we're going to do this without being given certain zeros. We're going to figure out how to start it on our own, and also how to find additional zeros that we don't necessarily get from factoring. So before we do that, we need to talk about a couple different sets of numbers just to help you guys be familiar with some vocab you'll hear today, and also just to make you familiar with some vocab you may hear later on. So when it comes to numbers, there's a lot of different sets of numbers. The one you've probably seen the most often, if you guys look at that R that's in that script, you guys are maybe used to writing that R like that. And you wrote that when you talked about domain and range a lot of times, when you wanted to write with less ink and not have to write out as much. That R there stands for the set of all real numbers. In real numbers is basically every possible number that's not imaginary. So what we're going to do, the real numbers is actually the largest of all these sets we're going to look at. So I'm going to start with the first one on here, which is n. N stands for the set of all natural numbers. And what natural numbers are whole positive numbers. So numbers like 1, 2, 17, 23. Those are our natural numbers. Then Z is our set of all integers. And integers are also whole numbers, but they also include negatives. So integers include all the natural numbers, but also include -1, -7, but they're still whole numbers. Q is where we can start to include some other numbers. Q includes is what we refer to as rational numbers, and we're going to talk about rational numbers today. You guys have learned about rational functions. Rational functions is when you have a function divided by a function. Very similar, a rational number is when you have a number divided by another number. So it's in the form of p over q. You're able to write it as a number over another number. So something like 1/2 is also a rational number. Any whole number is also rational because you could write it over 1. So 7 is because you can write 7 over 1. You also could write it as a decimal because 0.25 can be written as 1 over 4, which is a rational number. What rational numbers do not include are things such as square roots. Something like the square root of 3 is not a rational number because you can't ever write that value as a fraction. Another example of not being a rational number would be something like pi. Pi is not a rational number because even though you can estimate it with 22 over 7, there isn't an exact fraction that's equivalent to it. So because we can't write these as one number divided by another, they're not rational. But all of those values fall under real numbers. The only things that don't fall under real numbers are complex numbers and imaginary numbers, which we're going to look at tomorrow. So if you guys look, this little set here kind of shows how these tie in together. So the real numbers is the largest set and includes everything. Positives, negatives, something that you're able to divide by, pi, e, square roots. Rational numbers do include those fractions. Natural numbers, though, only include your positive whole numbers. So what we're going to do is we're going to use something called the rational zero theorem to find the possible rational zeros of a polynomial. Okay, so again, this is the reason we talked about what a rational number was. So this will help us find zeros, any zeros basically that we couldn't find without the quadratic formula. So if there was a zero such as 1 plus the square root of 3, or the square root of 25, or, well, square root of 25 would be 5, so we can find that, but a square root that we couldn't find another way, the rational zero theorem isn't going to necessarily help us with those, but it's going to help us find some of our factors. All right, so in order to do, the rational theorem tells us that we can find all of the possibilities. So it's not going to tell us exactly which ones are. We're going to use some of what we learned yesterday to determine that. But what we're going to do is find the possibles. So P stands for the factors of the constant term. So if you remember, the constant term is the number without any variables. So usually it's the last number in our equation. Then Q is the factors of the leading coefficient, which is usually the one that's written first, but it's the coefficient of the highest degree term. So in order to find the in order to find the rational zeros here, I'm going to find P. So P is -8, and I'm going to find the factors of P. So 8, or -8, is divisible by 1, 2, 4, and 8. But I can get this as any combination of positives and negatives, so all of these are plus or minus. So 1, 2, 4, and 8 are all the possibilities for factors of p. So now we're going to find the factors of q. Those are the factors of the leading coefficient. So that would be plus or minus 1, plus or minus 2, and plus and minus 4. Again, it's still positive and negative because a negative 1 times a negative 4 would still give me a positive 4. So then what I do is I find p over q. When I do p, every p value divided by every q value. So the first one here, I think it's usually easiest to start with each p and divide each p by every q. So what I'm going to do is I'm going to take the first p, which is 1. So I'll do 1 divided by 1, 1 divided by 2, whoops, that was 2 divided by 1, 1 divided by 2, and 1 divided by 4. Then I'll move to the next one, 2 divided by 1. But when I do 2 divided by 2, that value is already listed, so I don't need to list it again. Then I do 2 divided by 4, that's also already listed. So sometimes you'll get some duplicates, and you only have to write it that first time. Then I move on to the next p-value, which is 4. 4 divided by 1. 4 divided by 2 is already on my list. 4 divided by 4 is already on my list. And then I go to 8. 8 over 2 and 8 over 4 are already there. So these are all of the possible rational zeros of this graph. So what that means is that there will be no other rational zeros for that polynomial. Now there could be, like I said, there could be some square roots that are zeros and things like that, but we're not going to have any more rational ones. Now the reason this matters is the rational zero theorem helps us to factor something like we factored yesterday without giving the starting number. So in order to factor this without the starting number, what we're going to do is find the possibilities for the factors of 6, or for the factors of p over q's. So I'm going to find all the possible rational zeros. So the possible rational zeros, I'm going to find the factors of 6, so those are my p, so that's plus or minus 1, 2, 3, and 6. Factors of q would be 1 and 2. So the possibilities here are 1 divided by 1, 1 divided by 2, 2 divided by 1, 2 divided by 2 is already on there. Then I've got 3 divided by 2, 6 divided by 1, oh, I left off 3, 6 divided by 1, and 6 over 2 is already on there. So those are all the possible rational zeros. So what we're going to do is determine which one of these that actually is a zero. Okay, now in order to figure this out, we're going to use what we learned with the factor and remainder theorem. So if I do synthetic division with one of these numbers, I'll be able to prove it's a factor if I get 0 as a remainder. So let's try one for example. So let's do number 1. Let's just try positive 1. So I'm going to do synthetic division. So I have 1 here. So I've got 2, 1, negative 13, and 6. And I'm going to do synthetic division. So I bring down 2, and then I multiply and add, multiply and add, multiply and add. And I do not get a remainder of 0, which means that 1 is not a 0 of this equation, which means x minus 1 is not a factor. So since that didn't work, I'm going to move on and I'm going to try another 0. So I could pick any other value on here. So if there's a lot of possibilities, this can be a really tedious process because you do have to keep going until you get one correct. But a lot of times if you start with 1s, negative 1s, and 2s and negative 2s, a lot of times it's pretty common and you'll get one. So let's go ahead and try 2. So we'll just erase this and let's start over with 2. So I'll have 2, 1, negative 13, and 6. I'm going to bring down the first number, multiply, and add, multiply, and add, multiply, and add, and I do get 0 as a remainder. So what that means is that 2 is a 0 of this function, which also means x minus 2 is a function. Now the reason we do synthetic division instead of simply plugging that value in, first of all, it's a little bit simpler math, but second of all, the remaining function, so we start 1 degree less, so I'd have 2x squared plus 5x minus 3. That remaining function I can factor as well to find my additional zeros. So what I have here then is something I know how to factor. So I can do 2 times negative 3 and get negative 6. I'm going to rewrite this over here when I have some more space. So I've got 2x squared plus 6x minus x minus 3. I take out my 2x. I take out the 1. I'm sorry, that should have been a plus. And this factors into 2x minus 1 and x plus 3, which means my entire original equation, I do need to include the 2, which means I also have the factor of x minus 2. So now I've factored that complete original equation. Alright, so now what we're going to do is not just find the rational zeros and factor, we're going to find all of the real zeros on this equation. And what we'll do after we talk about complex numbers is we'll find all of the zeros, real and imaginary. But for right now, we're just going to find the real zeros. So the process here is going to start off the same. I'm going to find my p's and q's. And this time it'll be a little bit easier since my q value is just 1. There's only going to be the factors of 12. So I've got plus or minus 1, 2, 3, 4, 6, and 12. And I'm going to try one of these, and just for the sake of time, I'm going to go ahead and pick 3, because I have a feeling it might work since I know the answer. And I'm going to do synthetic division. And surprise, surprise, it does work. So I get 0 as a remainder, which means 3 is a 0 of that function. But if I look at the remaining function that's left, this time, what I have left I can't factor, because there aren't any numbers that multiply to a negative 4 and add to a negative 2. So we had to solve this quadratic equation for the zeros a different way. And you guys remember the other way you can solve quadratics, you can either complete the square or the quadratic formula. So I'm going to go ahead and use quadratic formula because a lot of us are more familiar with that. So it's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And I'm just going to go ahead and simplify this. So that's going to give me 2 plus or minus the square root of 4 plus 16, so it's 4 minus a negative 16. So it's 2 plus or minus the square root of 20 over 2. And I can simplify the square root of 20. The square root of 20 simplifies into 2 root 5. So I have 2 plus or minus 2 root 5 over 2. And since both terms at the top have a 2, I can go ahead and divide by that 2 at the bottom. Remember, since I'm adding those two terms, I do need to make sure they're both divisible by 2. I can't just split one of them up. So that gives me 1 plus or minus the square root of 5. So this means I have 3 zeros here. So I have the original 3 that I found using synthetic division. Don't forget that is included. If we find that we get zeros remainder, that is one of our zeros. So don't do all this work and forget it in the final answer. Then I have 1 plus the square root of 5, and I have 1 minus the square root of 5. And that's all for today. So we'll do a couple of these in class, and don't get discouraged if some of them are a little bit tedious. A lot of them won't be too large. You won't have a lot of numbers you'll have to guess and check with. But it'll be some extra good practice for you guys on synthetic division.